The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker is James Baty. He's the Managing Director for the Concrete Foundations Association and the Technical Director for the Tilt-Up Concrete Association. For more than 2 decades, he has been involved in concrete performance and energy efficiency for the concrete industry. He currently serves as a chair for ACI's Residential Concrete Code Committee 332 and is a voting member of 306, C650, and the new Certification Committee C655. I'd like to welcome James Baty.
That's it. Thank you. Well, with an introduction like that, you probably think this is going to be kind of a crazy presentation. I'm not Baty. I'm actually Baty, but that's okay. It's a 50-50 chance. You get one of either one. Probably one of the hardest tasks is to follow Ken Hover. And so, the man just has watts of energy, and there's nothing else to say about that. But what he did allude to the fact that he would start out a very pragmatic series of presentations, and that's the field that I come from, managing one of the concrete associations. I deal with contractors that are out in the field, having to work with the guidelines and the specifications and the code requirements for our industry. And cold weather is one of those that's been most cumbersome and most concerning for the industries. Back in the start of this millennium, 2001, maybe even going back into 99 and 98 a little bit, but certainly moving forward, we saw the application of cold weather practice, cold weather prevention to contractors showing up quite regularly. And it was different in every state. And so what that means to me is I end up on the phone an awful lot with many questions about why I'm not able to place concrete today. It's 45 degrees in Lexington, Kentucky. Why am I not able to place concrete today? It's 50 degrees in Atlanta, Georgia. Why did I hear a buddy of mine placing concrete at -5 in Lansing, Michigan? And so from an industry perspective, there's a lot of variation. So the CFA, Concrete Foundations Association, devised a look at the performance of cold weather concrete specific to the primary form of its application, cast in place residential foundation walls. So I'm going to walk you through some of that research. 20 minutes is really not enough time to do it justice, so I will tell you that there's a form of this presentation as a webinar that I can make available to you. I tend to give that webinar as we head into the winter months, so in the fall, like starting in September, October, November, I usually give it for free online 3 or 4 times, so you can always check in with us through our web domain. But the research was focused in 3 phases. We first wanted to get an assessment for the performance of mixed variation. We did that teaming with Master Builders Laboratory. We did well over 650 cylinders from a variety of different mixes that I'll show you how we got to that. And to really begin to get a sense for the change of calcium chloride, non-chloride accelerators, no presence for an accelerator, the different types of cements, primarily 1 and 3, and then also increasing the amount of cement content in those mixes, and how would that affect the behavior of maturity, concrete gaining strength throughout those cylinders. We would then take those cylinders, move into some full-scale wall samples from selected components that gave us a nice range from economic mixes to souped-up mixes, so that we could begin to develop variation for the contractor, selectability, and also regional variance in mix designs. And then ultimately we needed to answer the question that was on the mind of every inspector that wanted to slow down or to shut down a job site in how is the performance of that cold weather concrete going to affect the durability? what is the building owner, what is the homeowner going to get when we walk away and that concrete has frozen or remained cold for a period of time. And so those were kind of on our minds. An excellent team was assembled. You see some variations there from, we had a research leader, a PE that was involved in establishing the research and monitoring it all the way through. Several supplier members, Concure, you're going to hear several times today, was involved in Semstone Concrete. And then we had a wealth of contractors that were contributing their time, their labor, and ready-mix providers as well, so that we could get the whole job done. So that team designed the research, and as I said, it's kind of a response to the market is really what got us here. We saw just incredible regional variations, and the simple idea that at the same moment, the same winter, the same week, we could see concrete literally not being placed, as I said, in Atlanta, Georgia, North Carolina, Kentucky, in the 40 to 50 ranges, but still sub-freezing conditions in the teens, maybe even in Michigan, was really a dramatic reason for us entering into that research. Up in Anchorage, Alaska was kind of a featured spot for us because we had a contractor where their building department would require them to tent and auxiliary heat any residential foundation installed below 35 degrees until they could determine or prove that the concrete was at 1,500 psi concrete, 1,500 psi strength. So it was a significant cost that some contractors were having to add to their cold weather production. So the precipice for the research really is how cold is cold? What happens in cold weather, and what can we do to design around it and continue to improve the practice of cold weather concrete? Existing codes, guides, and specifications really were excessive in terms of application then to the contractors, were excessive in both measure and the empirical evidence that is out in the field versus the relationship to 306, for instance, showed a departure of some 50 to 70 years of monitoring and empirical placement practice that evidence of a better performance than what we were currently giving concrete credit for. So let's look at the different phases of the research. Phase one, as I said, laboratory chillers, over 650 cylinders, representing 36 different mixtures, 44 maturity curves because we did some of those at 50 degrees and some of those at 30 degrees. We really wanted to prove to Atlanta that 50 degrees isn't cold. Being from Iowa, we know that's not the case. And the mixes are going to, as I'm showing you the mixes, they do range from a lean to a rich mix so that we could get an assessment for practical steps that you can do when you see target temperatures coming your way. And then when we moved into the field, again, the 6 selected mix designs, we blanketed some walls, we didn't blanket some walls, and then phase 3 was the Petrography to determine durability. So this is how we got to our mixes. The cements ranged from 5 to 6.5 sacks per cubic yard. They were all type 1 or type 3 cements. They all used each of those components then were mixed with admixtures, 1%, 2% calcium, 1% calcium with a mid-range water reducer, as well as a non-chloride accelerator master builder's product. And then the majority of the mixes, 36 of them at 30 degrees, and then we had 8 of them at 50 degrees. So you do the math on all of that, and you come up with the 44 maturity curves. So looking at just some of the research so that you can get a sense for the task that was undertaken. This is the 30-degree chiller, and you can see the different batches laid out. And at the front of each batch, where there's the double cylinder right in front of a row of 3, you'll see the temperature probes that were inserted into one cylinder for each batch so that we could monitor accurately the concrete temperature. This was an important part of our research as we wanted to directly correlate the mix performance at those temperatures to a computer model that we could then accurately predict in the field what our maturity was. You know the temperature curve that you're expecting, you know the concrete mix design, you've proven its maturity curve relationship, you apply those in a computer and you can determine at what point do you need to remove protection, at what point do you need to provide protection, because maybe you got into a situation where you weren't predicting a cold weather snap, and so that can be used to more accurately decide what your plan is for a particular placement. When we went outside, we got the best of all worlds. Now, First of all, if I go back just a moment to the chiller, you'll notice that this is a cold weather chiller. It's 30 degrees. It's held at 30 degrees. It's not ASTM moist cure 70 degree cylinder testing. So we were really abusing the concrete from the start in our phase one, and we really did it some justice when we got outside. And this is the environment that our contractors are facing, and there's an economic impact in not being able to place concrete in these conditions. Builders are wanting the houses to turn. Homeowners are ready for their home. And if you have to wait 3 weeks or 2 days or whatever the delay is going to be, there's a significant impact to the economic flow of those projects. When we started the placement, wall number 1 up there in the upper left, visibly snowing. It was cold. I'll show you the daily temperature range at the time. And the temperature was falling, and Ken will appreciate there's no sunshine, so had somebody been out there with a handheld infrared, we've been relatively accurate with our temperatures. Our concrete temperatures, everything was mixed indoors, everything was heated, all of our aggregate concrete was delivered at 65-degree target temperatures. So we wanted to simulate what the environment was going to be at a placement of this nature. And we even had the benefit of a semi-excavation feel. You can see at the ready-mix supplier, the block retaining wall that they have behind there kind of protects it from prevailing winds, much like an excavation in a residential foundation might be. So we proceeded through, and the mixes, so that's actually mix 3 on the very top up there, and you have mix 3 placed in 2 walls. You see the 2x4 that's coming down the left-hand side of walls. That's where the blankets are going to roll up, and we really just took a 6-foot blanket, capped the top of the wall, and did not take the blanket all the way to what would be footer to footer if we were in an excavation. There you can see the blanket in place, and through a carefully trained eye in the upper right, those 2 walls, you'll also see the temperature probes sitting in their plastic bags at the tops of the walls, and then there are also temperature probes at the midpoints of the walls. So we were trying to get an accurate assessment for the difference of the variation in evaporation, as well as exposure at concrete to air versus concrete to aluminum forms. So we have a lot of data, as you can imagine, and you're going to see a lot of data throughout, and you'll be tested on this at the end when we do Q&A. But just literally to kind of get a sense for the way that the research was designed. This is the graph from the phase 1 cold chillers, and so you have the mixes 1 through 44 on the very far left. And we were measuring initial set, final set, 1 day age, 2 day age, 3 days, 7 day, 14, 28, all the way out to 180 days. So we really were trying to get an accurate assessment at a maintained 30-degree temperature how these concrete mixes would perform. So in essence, at the time that we built this research, we really felt that this was designed to worst case scenario. We could not design a more appropriate way to measure the impact of maintained cold temperatures on concrete maturity in a lab scenario. We certainly could not have imagined much worse of a case, or wanted to endure, maybe I should say that, endure much worse of a case in our field studies. So the concrete was really it wasn't babied. It wasn't set up to succeed. It was set up to fail. We wanted to see what the true performance of that concrete would be as it relates to the environment. And this is an example of what we found at the site. And this is the weather data, OSHA weather data for Cleveland, Ohio, which is where our research was done, beginning January 10th, 2003. You can see that the high for the day was 33 degrees. The average was 27. We were placing, and when they started placement of that concrete, it was in the 31 to 32 range and falling. And then, if you can read that chart, beginning on the 10th, it never got above freezing for 21 more days until the end of the month. And on the 31st of January, it finally got back above freezing, 39 for the high, low of 12 and an average of 26. So this concrete, by most practical applications, was frozen for 21 days. It was certainly really, really cold. for 21 days. Because you'll see a lot of single digits right through the middle of that 21-day cycle. More about the physical test, the walls themselves, and really the lab data, the 650 cylinders in the lab, that was to set up what we would find on the field. It was to set up our computer models. It was used to validate the maturity method as an accurate prediction for concrete strength. This is where we really wanted to see the impact. And so you see the forming panels being removed from those walls. That was the next day. So some 24 to 30 hours. It was 24 to 30 hours, so just maybe a day and a half. After the concrete was placed, we removed those forming panels. So that concrete is also rather green at that point, even in a normal condition. I've got 5 minutes left? You're kidding me. All right, so you like that. All right. 5 minutes, wow, all right. So let's show you a little bit about the graphs, and you can get to me if you want more detail. But this is what a maturity graph is going to look like. This was our validation of the testing labs. It really seemed like Ken talked longer than 20 minutes. All right, so all right, thank you. Mix 29. So the Mix 3, Mix 29. These were two of the selected ones we took from the lab out to the job site. Just to show you the difference is Type 1 5-sac mix with 2% calcium. This is a Type 3 5.5-sac mix with 1% calcium. So you would expect higher strength. Type 3 cement, higher strength, should be a higher maturity, and you can see that the strength did gain at a rapid pace. What this research really allowed us to do was to look at the performance of all these different mixes and find one that we liked, or find one that we thought we could apply to a given situation. So these are all of the 5-sac mixes. With Type 1 and Type 3 cement. You have two Type 1 cements and two Type 3 cements. These are the 4 5-sac mixes with no admixtures. And we get a really good relationship of the impact of Type 3. And there's the 30 and 50 degrees represented there as well. So you would expect the 50-degree temperatures to mature at a higher rate. This is the 5-sac mixes with the varying amounts of admixtures, no admixture, 1%, 2%, 1% mid-range, and NCA. And so we can get a sense that the 1% with the mid-range, which is, and the non-chloride accelerator is the top two lines, and the 2% cal and the 1% and the no cal was clumped rather closely together there. This is just kind of to summarize the data for you, give you a layer looking at 5-sac, 5.5, 6 with the 2% cal and the 1% cal in a table showing you the difference between what the maturity prediction of each segment was along the bottom line. So if we look at 5.5 sac, Type 1, 2% cal, which is the second set of 3 lines there, the maturity prediction was 280, 580, 940, and 1690 at 1, 2, 3, and 7 days. And we were actually measuring in the field from the cylinders, or from the cores that were cut from these walls, 400, 590, 1,000, and 1815. So you can see that there's a pretty strong correlation between what the computer model predicted after we had done the lab studies, and then applying that to the field, what our prediction was truly going to be. This is just kind of showing you how we monitored it. So this is the unblanketed wall, top of wall in yellow, center of wall in black, and I'm going to lay that over with the blanketed wall. So we did get an idea that the blanket for a 24-hour period made a significant impact on maintaining the temperature. So now the top of wall, which is now the blue line of the blanketed sample, is significantly higher than what the top of the wall was for the unblanketed, and the center of wall is up above what the top of wall was. So from a contractor's perspective, a very simple application of a 6-foot blanket for the first 24-hour period in a cold weather snap gave them a good boost, a nice strength gain early on in the wall. The Petrography, just a simple graph showing you the difference between the unblanketed and blanketed walls. Again, the idea of a small blanket for the first 24-hour period, every single one of those mixes, 3, which was a very lean mix, to 34B, which is a very rather expensive and rich mix, all of them exhibited July-like concrete qualities. The petrographer's statement was, you could not have told me, if you hadn't have told me that these were winter samples, I would not have been able to tell you what time of the year these cores were taken from. The concrete was that solid, was that durable. And my last thing I'll say before I get pulled off the stage is that this research now allows contractors to take a look at target temperature conditions and to decide how long they have until a cold snap is coming, how long it takes them, or how long they need to have protection in place. And it's this type of a graph that allows them to be able to dial that in. All of the mixes along, this is just looking at the different rates to 500 psi. This is a ranked of the mixes from soonest to 500 psi to longest. And then we resort it to fastest to 1,000. So based on a specific project requirement or, again, a temperature condition that they might be looking out for, we can give them direction as to the type of mixes that they might employ. So we learned the concrete temperature is really the predictor. Ambient temperature influences it, but an inspector shouldn't be targeting a contractor or a stoppage of work based on what that ambient temperature is. We can truly design concrete performance to impact positively the project at any ambient temperature. Hydration doesn't stop at 40, which was a popular theory that we were hearing from the field, and maturity prediction can be used accurately. There's also no single mix is the answer. Pour early in the day. Type 3 is if you've got it in your market, Type 3 is expensive, but it's going to give you better performance over Type 1. Calcium chloride, when steel's not present in the structural application, is a great bang for your buck. So some of the things that contractors already knew, we were able to validate from this research, but then correlate it so that they can now use it and they could start to design new mixes with their ready mix producer or a fleet of mixes that they could use at temperature ranges. So with that, I guess you're going to want questions from me.
Yeah. Time for a few questions.
Really quick, why don't you write those down because you might want some follow-up data. Yes, sir.
You were saying earlier that you needed your aggregates and your water in this study, right? I'm from North Carolina. So I find it interesting that you put North Carolina up there. One of the issues that we have is nobody in our market needs aggregates. And also, I would say that well over 50% of the plants don't even have a hot water source for the winter. So what effect is non-heated aggregates and non-heated water going to have on concrete temperatures? And that you should take a look at that as to the effect that may have on strength.
We didn't in this research. We delivered all of our concrete as if it had been cold weather practice with facilities available to deliver target temperatures in the 65 temperature range. What you would get is a much closer delta T to ambient temperature for your delivery temperature. So you have to be more concerned about that hydration boost that you get after placement. And so what we did do, though, is validate the maturity method. So if you knew what your concrete temperature was and you knew what your ambient temperature prediction curve was, you can still correlate the data to the same research results that we have.
The last couple of winters we've had were very difficult. And one of the things that I can tell you is we have a very difficult time with plants that do not have hot water sources, even getting 50 degrees.
Sure. So what you would do is you'd want to take a look at those plants, and the contractors would want to take a look at what your availability is, and pick those mixes and the protection types to sustain those temperatures at a higher because you get a lower delta T.
And I will tell you that's why the code officials in North Carolina make a decision that they make.
Yeah.
So just understanding what draws the code officials enforcing what they do is a lot of the availability of the market.
Good point. Good point.
Do you know offhand what you use for a dating temperature for maturity graphs? It makes a big difference.
Yeah, we use the Arrhenius equation.
So did you use like -10?
No, the Arrhenius equation doesn't.
Oh, I'm sorry. Yeah, they're solid. Okay.
Yeah, and so what we did is when we calculated the maturity curves, we cured them under constant conditions at either 30 degrees or 50 degrees.
Yeah, this full research report is available from our website. 74-page result.